diagonal components ZMN. Let's say if I want to calculate what was ZMN. ZMN was integration from 0 to L bn y dash dy dash square root of, see, this is the basis function bn nth basis function, and what you have here is the distance between the source and observation point. We were observing along the axis of the y-axis, and A is the radius of the cylinder we are considering, cylindrical wire we are considering. And if you remember at the beginning, I have told that this radius of the cylinder A is very much lesser than the length of the cylinder L. L is very much greater than A. And in that case, we can actually neglect this term here. Then our integration simplifies to, anyway, one more thing is that when I do integration from 0 to L and Bn is having a value of 1 in the interval yn minus 1 to yn. Outside that interval is 0. That's the property of the pulse function we are using as a basis function. So the integration will be now from yn minus 1 to yn, and it is having, Bn is having a value of 1 in that portion. Outside that portion is 0. So integration simplifies to this, and A is a very small number. We assume that radius of the cylindrical wire is very small. In that case, A can be neglected. Then the integration reduced to this. And again, so this is square root of ym minus y dash. So when you take the square root, you just get ym minus y dash. So the integration we need to find ZMN is simply integration from yn minus 1 to yn dy dash by ym minus y dash. So now what is y dash? Y dash is a location of the source. So location of the source. Now you have one technique called centroidal approximation. In the integration centroidal approximation, what it means is that if I want to do the integration of a function, what I can do is I can simply find it out by multiplying the function with the interval size. Now interval size, we are making a subsection of delta. So this yn minus 1 to yn, how much is the length? Length is delta. So this is the interval size. You multiply with the function at the center. Centroidal approximation means you calculate this function. What is the function we are integrating? It's 1 by ym minus y dash. So if I want to apply this centroidal approximation, I just find out this function at the center. So at the center, what is the value of y dash? Y dash will become yn. So in that case, I just find out this function at the center and multiply by the interval. Then I get the function. So I use centroidal approximation, and I can do this integration simply as multiplication of delta divided by ym minus yn. So you don't have to do any integration now. So you can always find out ZMN as delta by ym minus yn. This is for the case when m not equal to n. That is for the off diagonal elements of the matrix like Z1 to Z1 and so on. There are some issues with the diagonal components. We'll discuss that in the next slide. So, see, basically, for these diagonal elements, your source and element are at the same location. Let me go back to the diagram so that you know what's going on. So now this is a diagram. We are doing subsection of this wire into n subsections. So this is first subsection, second, third, fourth, and so on. So what do I mean by of diagonal element and diagonal element? This is the observation point. We have two variables running. One is the source variable, which is r dash, and other observation variables are y1, y2 up to and so on. So when I say that diagonal element means, let's consider this subsection of the wire, and I'm making observation at this yn, and my source is also in this subsection here. So diagonal elements means my subsection for the source and the observation are at the same location. So this subsection here is the second subsection. So let's say if I want to find Z22, then Z22 means my source is also here inside this subsection, and even observation is also here inside this subsection. And you know that this is a cylindrical hollow wire, metallic conductor. So sources are on the surface of the wire. So sources are not there in this line here. So somehow we are very careful at the beginning itself so that my source and observation point are not at the same location. Have my observation and source at the same location. When you find the distance between them, it will become 0. So 1 by 0 will become infinite. So that is called singularity effect. When you calculate the diagonal elements of the Z matrix, since your source and observation point are at the same location, your integration will become infinite. It will become singular. You cannot do the integration. But here we have carefully chosen the observation point along the y-axis so that even if we are at the same subsection 2 for the source and observation, my observation is along the y-axis, but source is on the surface of the wire, so they are not at the same location now. So because of that, it will not become infinite. So we have carefully chosen the observation so that we don't get that singularity effect here. So the problem with the diagonal element is that your source and observation point are at the same location. So you'll have infinite value of the, see, you just go back to this. Let's say if I want to use this expression for Zmn by employing this formula delta by Ym minus Yn. So now in this case, Ym and Yn are at the same location. In that case, this will become infinite, so I will not get a finite value of the Zmn. So this is a singularity effect. So I have to be extra careful when I am calculating the diagonal elements. And you'll see that later on, diagonal elements are the major contribution of this Z matrix, because source and observation are very near in this case. So let's say if you want to calculate the diagonal elements when m is equal to n, in that case, you have to take care of the singularity effect. For that, you can directly do integration here. For example, if I substitute Ym minus Y dash, which is there in the denominator Ym minus Y dash, if I substitute it as xi, it's substituted xi, then d xi, delta of xi will become minus dy dash. You substitute it, then the integration, this limit will also change now. It will from delta to 0. You'll have a negative sign because of this negative sign here. You can directly do the integration. So when you do integration of this expression, you get log of xi plus square root of xi square plus a square. Interval is from 0 to lambda. I have make the change of the interval. It was from delta to 0. I will change it to 0 to delta. This negative sign will go away. Then you plug in value of 0 and delta as the limit. This is what you get for the diagonal elements. So in this case, diagonal elements is always fixed. Zmm would become log of natural log of delta plus delta square, square root of delta square plus a square by a. So we have calculated the diagonal elements, we have calculated the off diagonal elements, and we have also calculated what is the B matrix. I can find out the I matrix now. Just before that, when you calculate the Z matrix, you don't need to calculate the whole matrix. See, basically you can see that Z12 and Z21 is equal. When you interchange your source and observation point, you'll get the same value of the Z element. So you don't need to calculate all of this. For example, if you just calculate this first row, you can always rotate it first row, then you can get all other elements. So this is called symmetric Toeplitz matrix. So this is a symmetric Toeplitz matrix. So you can just calculate this first row and you can just interchange this and fill up the remaining elements of the matrix easily. This is, you started from Z11, Z12, and Z1n here. So you start from Z12 here, then and so on. You can do it. So you do the rotation and you. So here is the way of finding the other elements of the different rows. First row, you just find out from the first row, you can find out all other rows. Second row, third row, and fourth, and so on, using this relation here. So now you have the Z matrix. If you want to find the I matrix, you can take the inverse of the Z matrix, multiply with the B matrix, you get the I matrix. Once you have the I matrix, you can find out the unknown function. So this is the plot for your Z matrix. One is diagonal element, another is the off diagonal element. Z21 is off diagonal, Z11 is diagonal element. As you already know that diagonal element was constant. No? So diagonal element was constant, and so if you even increase the number of successions of the wire, see basically capital N, if you keep on increasing the, okay, this is the diagonal element, this is the off diagonal element. So diagonal elements, when you increase the number of subsections of the wire, see what was the formula? Formula was this. Delta plus square root of delta square plus a square by a log natural log of that. So when you keep on increasing the number of subsections, delta is let's say total length of the wire is L by capital N. If N is increasing, delta is going to change. So because of that, as you keep on increasing the number of subsections, this is the number of sections, x-axis is the number of subsections, y-axis is either your Z11 or Z12. So Z11 keep on decreasing, so it's not converging. So after, let's say at the starting it was very steep, the slope was very steep, then slowly it is converging. So around 100, it's almost remaining constant, but off diagonal remains always constant. So you need to go up to, let's say for this particular case, N is equal to 100 and more to get a convergent result. So once you have this Z matrix and B matrix, you can find the I matrix and plot the unknown. What was unknown for us? Unknown for us was the line charge density. So this is line charge density versus the length of the wire. Let's say length of the wire is 0 to 1. Line charge density is very low at the center of the wire and it's very high at the two ends of the wire. So you can find out the unknown line charge density of the wire by using matter of moments, but you cannot find it from the analytical solution. So using numerical methods, you can find out how is the line charge density of a line charge when you apply a potential of 1 volt on the wire. So now, as I already told you in the last class, if you want to find the Z matrix inversion, you have to first check the condition number of the matrix. For this particular case, I have checked the condition number. It's coming out to be around 7. So it's okay. So 7 is okay. If it is infinity, then it is 100, 200, then you cannot take the inverse directly. So for this case, condition number is 7 and is close to 1. So you can directly take the inverse and you can find out the unknown vector I vector. Okay. So this completes the example on the electrostatics. And in the last class, many of you are asking about the basis function. So we'll spend some time on the basis function because this is a very important part of the MoM. And if you know basis function, then you can easily apply it. There are some common basis functions which are used for any kind of problem. Those kind of basis function also we'll discuss. We'll also discuss some basis function which are called entire domain basis function, and another is called subdomain basis function. In the entire domain basis function, we'll have one single function for the whole solution space. Let's say you consider the wire length of L. In the entire domain case, I will just consider one basis function over the whole length of the wire. And I will try to find the solution using the MoM. But in the subdomain basis function, I will subsection the wire into small subsections, n subsections, and represent over each subsection small subsections by some basis function. So this is a subdomain basis function. Entire domain basis function means over the whole wire, I will just assume one function and find the MoM to find the unknown function. But for a subdomain, I will subsection the entire wire into small subsections like we have done just now and assume every portion is small subsection by one pulse function. So this is a subdomain basis function. In the olden days, people used to use entire domain basis function also. In the entire domain basis function, it will be very quick. You just have one basis function for the whole solution space. But then you have to have an idea of what kind of solution you will be getting. So just look at the structure you are analyzing, let's say antenna or any scatterer. You know that what kind of current density that antenna or the scatterer will be having beforehand, looking at the structure. So you need to become an expert in electromagnetics. Will have an idea of what kind of solution you'll be getting beforehand and apply those kind of similar kind of basis function and find the solution. So this is called inter-domain function and it's very fast, quick, but then you need to have knowledge of the proper analysis of the structure you are analyzing. You would be able to guess what kind of function you will be getting from the analysis. But for a subdomain basis function, you don't need to know anything about what is the solution of the electromagnetic problems. You can apply it for any kind of problems. So let's look at some of the entire domain basis function. As I already told you, this entire domain basis function has span from minus L by 2 to plus L by 2 or 0 to L. Some examples are well known. For example, for a entire domain basis function would be cosine of n minus 1 by 2 to x by L. L is the total length of the solution space. You can also have Chebyshev basis function. We'll discuss about this Chebyshev polynomials, legendary polynomials also you can have as a basis function. depending on the problem you are analyzing, you have to choose a particular suitable inter-domain basis function. So these are some of the typical basis functions you can think of. So let's look at Chebyshev function. What is Chebyshev function? Chebyshev function is the solution of the Chebyshev differential equation. And I think all of you must be knowing this Chebyshev differential equations. People usually learn this in the second year of their undergraduate studies. You can solve this Chebyshev differential equation by power series expansion method. So this is the equation 1 minus x squared y double dash. Double dash means we are doing double differentiation of y with respect to x. Y dash means we are doing single dy by dx. This is del squared by y by del x squared. N is a real number. So this equation, Chebyshev differential equation, you find a solution of that. The solution you are getting is called Chebyshev functions of degree n. Here n is a real number. But let's say if you want to find it only for n is a positive integer. N is a positive integer, non-negative integer. In that case, this Chebyshev function, we call it as Chebyshev polynomials. And Chebyshev polynomial can be easily found out by using this recursive relation. So Chebyshev polynomials are usually denoted by Tn. So if I want to find Tn plus 1, then I use the value of Tn and Tn minus 1. So I multiply Tn with 2x and subtract Tn minus 1, then I get Tn plus 1. So now if I just have T0x and T1x, then I can find out all the values of Tn for any value of n greater than 1. So T0x is 1, T1x is x. So let's say if I want to find T2x, T2x will be n is equal to 1. So T2x is equal to 2x into T1x minus T0x. So what was T1x is x here. So 2x squared minus 1. So T2x will be 2x squared minus 1. From there you can find out T3x, T4x and so on. So this is how you find the Chebyshev polynomial using this recursive relation. Similarly, if you want to find Legendre's polynomial, you have to go back to the Legendre's differential equation. This is the Legendre differential equation. N is a real number, and the solution is called Legendre function of degree n. But when n is a non-negative integer, we call this as Legendre polynomial. So Legendre polynomial also can be easily found out from this recursive relation. We usually denote Legendre polynomial by Pn. So if I want to find Pn plus 1, I have to know what is Pn and Pn minus 1. Using this relation, I can find out Pn plus 1. So if I have P0x is 1, P1x is x, I can always find out P2x, P3x, and so on using this recursive relation. So let's say if I want to find P2x, n would be 1, so 2 into n is 1, so P2x, then n is 1, so 2n plus 1 will become 3x, then what is this? This is x minus n is 1, then this is 1. So you get the value of the P2x from P1x and P0x. So the problem with this inter-domain basis function is that you have to be an expert in the electromagnetic fields and you should be able to guess. For example, let's say you have a problem and beforehand you have to say that the solution would be like Legendre functions, like Legendre polynomials, or let's say Chebyshev polynomials. You should be able to tell what is the solution beforehand. So that is very difficult for the persons who are starting this MoM techniques, and only for expert can do that. If you do that, then it becomes very powerful. It's very fast. Only one element is there. So let's say, but you want to develop a general purpose MoM based software, like we have discussed in the first lecture. We have Sonnet, which is MoM based software. Then i3D, this is MoM based software. FEKO, these are all MoM based software. If you want to develop a general purpose MoM based software which can analyze any kind of problem, then you have to go for the subdomain basis function. Subdomain basis function can be applied for any general purpose. So let's look at what kind of subdomain basis function. We have already discussed one of them, which is the pulse function. Pulse function usually have a value of 1 over the interval, and outside the interval becomes 0. And I have already told you what is the problem with the pulse function. If you have a boundary where your unknown function is 0, you cannot model those kind of boundary. Another basis function is called piecewise triangular function. Let me show you the diagram first so that you know what's. This is a pulse function. So over the interval xn minus 1 to xn plus 1, this pulse function is having a value of 1. Outside that, it becomes 0. This is a triangular basis function. You have one line here, another line here. So you have a line with a positive slope here. You have another line with a negative slope here. So you have to write the equation of this line and you have to write the equation of this line. Over the interval, so this line is over the interval xn minus 1 to xn. This line is over the interval xn to xn plus 1. So how do I write that equation? And you can observe that this piecewise triangular function is having a span of 2 intervals. So this is delta, this is delta. We are actually having a triangular basis function which is over 2 delta. And over this xn minus 1 to xn, we have a positive line, a line with positive slope. Over to xn plus 1, we have another line with the negative slope. Why we are having this overlapping piecewise triangular function? We'll discuss that later on. It's easier for us to model the unknown functions more properly. This is actually, so let's first find out the equation for this triangular basis function first. So if I want to write a line with a positive slope, I should have positive value of x here. So this is the equation. Over xn minus 1 to xn, I have a line with positive slope. X minus xn minus 1 divided by xn minus 1. This is delta here. X minus xn minus 1 by delta. So that's the equation of the line with the positive slope in the first interval. In the second interval, you have a line with a negative slope from xn to xn plus 1. So that would be xn plus 1 minus x. Minus x, because of this, you have a negative slope divided by delta. 0 otherwise. Outside these two intervals, it becomes 0. If you want to use modulus and write this in more compact form, the basis function, triangular basis function, will be delta minus xn modulus divided by delta over the interval xn minus 1 to xn plus 1. So this is the equation for the piecewise triangular function. From the piecewise triangular function, if you want to write the piecewise sinusoidal function, you just take sine of this, then you will get it. This equation here, the piecewise triangular function, you take sine of this, you get the piecewise sinusoidal function. So they are related. So I take sine of this divided by sine of this. So I take sine of this, I take sine of this. I also multiply by a constant k here. So this k is going to change depending on the medium you are considering. If it is a dielectric, this k value will change. If it is a free space, k value will change. So depending on that, I have a control over this sine function. Let's say you are modeling a structure where you have a free space also, you have a dielectric also. This k value for the piecewise sinusoidal will change depending on whether you have a dielectric or a free space. You can also write in compact form as sine k times del minus xn divided by sine of k delta. So if you know this expression, you just multiply by k here, take sine of that, you get the piecewise sinusoidal function. So the problem with the pulse function, I have already mentioned, one was the boundary condition. Another thing is that when you take the integration of this pulse function, what happens to this point here? This point has a discontinuity here, this point has a discontinuity here. So you'll have infinite value here over the differentiation. If I have an integral differential equation in which I have a derivative, then I cannot use this pulse function because this is discontinuous. So usually the most commonly used basis function are either triangular basis function or piecewise sinusoidal basis function. And you know that in the wire antennas, your fields were sinusoidal. We have already drawn the current distribution on wire antennas like dipole antennas in the previous semester. What you have observed was all the functions were sinusoidal. In that case, you can use piecewise sinusoidal. Or you can even use triangular basis function, it doesn't matter. So piecewise sinusoidal function and triangular basis function can be applied for any kind of problems. Okay. So in order to familiarize yourself with the basis function, I have given some assignment here. This is the second assignment. Just before that, we have this piecewise triangular and sinusoidal basis function. Now let's say you have a wire, you subsection it into n points. How many subsections you will have? N minus 1 subsections. But now you are considering overlapping case. No? So this triangular basis function is going from here to here. Again, you have another triangular basis function starting from here. This is a triangular basis function. So you have another triangular basis function here, another triangular basis function here, another triangular basis function here. Here also. So we are considering overlapping piecewise triangular and piecewise sinusoidal functions. Why we are doing that, I will show you, I think, at the end of this lecture. I will draw some diagrams and tell you why we are having this kind of. It's easier for us to model the unknown basis function, unknown functions. So your second home exercise is you plot this inter-domain and subdomain basis functions so that you remember clearly. It should be there in your mind. What are the possible inter-domain basis functions, subdomain basis function? Just to make you remember this basis function, it should be there in mind. So I have given an assignment to plot this basis function. Let's say you plot Chebyshev function or Chebyshev polynomial of order n is equal to 5. Use the recursive relation. You find out what is the Chebyshev polynomial of order 5 and use the recursive relation for legendary case, and you find out the legendary function of order 3. You plot those functions. And you can also plot this piecewise constant and piecewise triangular and piecewise sinusoidal function. The expressions are given, you just plot it. The expressions are there, no? I have already discussed that. This one expression, this is another expression, you plot it. In MATLAB, no? You can plot it easily. This is the recursive relation for the legendary polynomial. You find out P3 from here. And you find out T5 from here, you plot it. So when you do that, you'll remember the functions and you'll get to know it better. No? Any questions here? Otherwise, I'll start the next part. So any questions in the basis functions? We'll start with the wire antennas and scatter, otherwise. Okay, so the example we have considered was for the electrostatic case. We have considered a simple case of differential equation. We have also considered the electrostatic case. But MoM is widely used for antennas and scatterers, which are purely electrodynamic fields. They are not electrostatic case, electrodynamic fields they are. So let us consider some of them. So, and see, the antenna and scatterer, it's how you look at it. No? So basically, antenna and scatterers are very similar. So let's say you have a source which is an antenna. You supply some, so antenna is a passive device. You supply some source to the antenna, it will start radiating. So the process is usually, let's say if you have a metal antenna, conductor-based antenna, some current will be flowing on the conducting surface of the antenna, and then current will start radiating fields. So if you are having some time-bearing currents, then time-bearing currents from the fundamental law of electromagnetic radiation, it will start radiating fields everywhere in space. But let's say you consider, for example, antenna as a transmitter, antenna as a receiver. For example, in the receiver case, what you have is fields are incident on the antenna. From that incident field, some current will be induced on the antenna surface, and that would be actually used for receiving the signals. And moreover, let's say you have some conductors which are placed on the path of the electromagnetic waves. It will also scatter the waves. So the analysis for the antenna and scatterers is very similar, but we'll consider the antenna case, wire antenna, and try to find out the MoM for wire antenna. Simplest case is, let's say, dipole antenna. So first thing is you have to derive the integral equation and solve that integral equation using the MoM. And most of the time, MoM is very popular for solving integral equation. And integral equation doesn't have closed form analytical solutions. So first thing is you actually derive the integral equation for the wire antenna and you solve it using the MoM. So for the wire antennas, the first thing is that you know what is the feed voltage, how much voltage we are giving, supplying to the antenna. From there, you can calculate the current distribution, and once you have the, so unknown thing is the current distribution. How much source you are applying, how much voltage you are applying to the antenna is known to you, because this is what you have given to the antenna. Source you are giving to the antenna, you know how much you are giving. So how much is what is the current distribution on the antenna is not known to you, so that is unknown. So once you have the current density on the antenna, you know almost everything about the antenna, because you can find all other antenna parameters like impedance, bandwidth, radiation pattern, everything from the current distribution. So the current distribution is the unknown for most of the MoM case, and you can solve it by using MoM. First write the integral equation, solve it using the MoM and find out the current distribution, then you can find all other antenna parameters. Okay, so let us try to write the integral equation first. That's the first step. Write down the electric field integral equation for this particular case. Let's say if you have a perfect conductor, what is the boundary condition on the perfect conductor? Boundary condition on the perfect conductor is that tensile component of the electric field is 0. So here you will have two kinds of field. One is the incident electric field, another is the scattered electric field. Incident electric field is the impressed field you are giving to the antenna. Because of that, you will also have some scattered electric field. So the total tangential electric field should be equal to 0, which is actually composed of two parts. One is the incident field, another is the scattered field. So E incident, so this is equal to 0, so E incident should be equal to E scattered, only the tangential components. So this is called electric field integral equation. So this is a wire antenna, this is a dipole antenna, you have a conductor here, cylindrical conductor here, this is the upper arm of the dipole, this is the lower arm of the dipole. So you have a feed gap here, which at a distance of 2 delta, you supply some source here to this antenna. If you are supplying some time bearing current, then it will start radiating. The radius of the cylinder is A and length of the wire antenna is A here, L here. So like last time, I consider A is very much lesser than L. This feed gap is of 2 delta. So here you supply the voltage to the antenna. There are two different kinds of integral equation. One is called Heron's equation, another is Polynomial's equation. Both of them are very much related. We'll try to derive that. So first we derive the integral equation and we'll try to solve it using MoM. So there are different models for the feed gap, how you are supplying the voltage to the antenna. The simplest model is called, you assume that the voltage you are applying is B0 and how much is the, see, if you know what is the voltage applied, then you know how much is the electric current, what is the electric field. Electric field and voltage, you know the relation, no? You multiply delta with the electric field, you will get the voltage. So in this model, we assume that the electric field which is induced incident on the antenna is actually because of the voltage you are applying. So in the upper arm, you are giving a voltage of, let's say you are giving a voltage of B0 plus and B0 minus in the upper one and lower one. So how much is the voltage difference? Voltage difference is 2B naught. How much is the distance? Distance is 2 lambda. So if I want to find the electric field and assume that electric field is uniform in that gap, in the feed gap. So we are actually assuming that electric field which is incident on this feed gap is uniform because this 2 delta is very small. 2 delta is very small. So in that case, electric field can be assumed uniform along this. And you can calculate it. So voltage applied is B0 plus and B0 minus to B0 divided by distance is 2 lambda. So the incident electric field, and we are positioning this wire along the z-axis, the incident electric field in this area is basically having only z component and it is B0 by delta. So outside this area, we don't have any incident electric field. This is the simplest model for the wire antenna. This is called feed gap model. So you assume that this is the incident electric field. I know what is the incident electric field. I want to calculate the scattered electric field because of this incident electric field. So this field is incident on the antenna. Because of that, we'll actually have some scattered electric field. So how do I find this scattered electric field? And you know that total electric field is composed of incident electric field and scattered electric field. I want to find this scattered electric field. Since my incident electric field is along the z-axis, I can also assume that scattered electric field is also along the z-axis. And you look at this wire here. If your field is along the z-axis, you can observe that field is tangential field. this is a conductor you have here, cylindrical conductor here. Any field along the z-axis would be always tangential to this conductor here. So all of them are tangential electric fields. So E total along the z-axis, which is a tangential field, would be E incident plus E scattered, and it should be equal to 0 on the wire antenna because wire antenna is a conductor. Then you can also write Ez scattered is equal to minus Ez incident. So you will have to go back to your electromagnetic field theory. If I have electrodynamic fields, how do I find electric fields? So in the electrostatics, I find electric field as negative gradient of the electric potential. But if you have electrodynamic fields, you will have one extra term here, which is called, for the electrodynamic fields, minus dou A by dou T. And if you have time harmonic fields, you can replace dou by dou T by j omega. So you can find electric field, this scattered electric field, as minus j omega magnetic vector potential minus negative gradient of the electric potential. You apply the Lorentz-Gauss condition. See, in the Lorentz-Gauss condition, you find the divergence of A. So divergence of A. So let's say if I want to find the curl of A, I can easily find out from the magnetic field. But I do not know the divergence of the magnetic vector potential. If I want to know everything about a vector, I need to know the divergence as well as the curl. So divergence, actually you get it from the Lorentz-Gauss condition. From the Lorentz-Gauss condition, divergence is equal to minus j omega mu naught epsilon 0 b. So you can plug it in here, you can find out what is electric field now. And if you want to find the electric field, you need to know the current density first, because you have magnetic vector potential here also. No? So current density, let us try to find out. So let's say if current flowing along the z-axis is Iz, and if I want to find the current density on the circumference of the cylindrical wire you have here, current density on the circumference of the cylindrical wire here, I need to just divide it by 2 pi a. So the current density which is flowing along the z-axis can be found out as Iz dash divided by 2 pi a. Z dash is for the source. You have a prime coordinates here. This is for the source. So you can actually equivalently model this cylindrical wire by a surface current density of Z dash, which is basically Iz dash by 2 pi. So now you can find out using this relation here and applying the Lorentz-Gauss condition, you can find out the electric field which has only Z component. Ez would be minus j omega Az minus dou b by dou z. This equation here. So this equation here, you use it, you find the electric field. For electrodynamic fields, you need to have this extra term here. Time harmonic fields, you have j omega here. Let's say electric field will have three components, x, y, and z. But for this case, we just want to know the z component. So z component of the scattered electric field. So Ez should be equal to minus j omega Az minus del b by del z. So we'll have only that for the z component. So this del b by del z also I can apply Lorentz-Gauss condition. What was Lorentz-Gauss condition? Del dot A is equal to j omega mu epsilon 0 b. So there also I will just have only one component because I'm interested in the z component. So I can find out minus dou b by dou z is 1 by j omega mu naught epsilon del square Az by del z square. So I can replace this. So in that case, I can find electric field only from the magnetic vector potential, which has z component. So this one is electric potential. I will replace it in terms of magnetic vector potential. Then Ez is totally dependent on Az. So we can find out Ez as minus j omega Az plus 1 by j omega mu naught epsilon 0 del square Az by del z square. You can simplify it, write it in this form here, where beta naught A square is omega square mu naught epsilon 0. So Ez is 1 by j omega mu naught epsilon 0 beta naught square Az plus del square Az by del z square. Is that okay? So we actually, if you have attended last semester course, we actually find electric field from the magnetic vector potential. It's easier for us to find because magnetic vector potential is easier to find from the electric field. How do I find the magnetic vector potential? I find it from the current density. So this is the expression you have, the relation between the current density and magnetic vector potential. If I want to find Az is mu naught Jz exponential minus j beta naught r divided by 4 pi r ds dash. We have already spent a lot of time in similar kind of things in the last semester. So if you are new to this course and you do not understand this, you can always discuss with me later on also. So AZ is basically you do the convolution of the Green's function for free space with the current density. So ZZ is the current density. From the ZZ, you can find out AZ. And your electric current density and magnetic vector potential has same direction. So when I have ZZ here, I will have AZ here. So you can find out AZ. So I want to find EZ is totally dependent on AZ. AZ can be found out like this. What was ZZ? ZZ was IZ by 2 pi A. You just plug in here. What is DS dash here? A d phi dash DZ dash. It's over the so A d phi dash is over the circumference, then over the total length of the wire, which is from minus L by T to plus L by T. Here you can find the distance between the source and observation. What is R here? R is the distance between source and observation point. Source is at location X, Y, Z with unprime coordinates, and prime coordinates is for the source. This for the observation. Distance between them you can find out. For rho is equal to A, you can write AZ is equal to, is it okay? So for rho is equal to A, you can find out what is this R. You can derive this. You can derive this. So I can just write R as square root of 4A square sine square phi dash by 2 plus Z minus Z dash whole square. So now I want to write everything in terms of the polar coordinates. I don't want to use any kind of, what is this? This is the Cartesian coordinates. I have converted everything in terms of polar coordinates, and this is a relation for the distance between the source and observation point in the polar coordinates. Because I have done the integration over the polar coordinates, d phi dash. So I want to write R in terms of phi. So the final expression AZ, if you look closely, then you can represent this as Green's function. So this is IZ, and you can say that this is a Green's function for the analysis wire antenna. So you can write AZ as IZ dash GZ comma GZ dash. This is basically your Green's function, which is this expression here. So this is a compact notation. I actually write AZ as the convolution of the current density and Green's function for this wire antenna. So as I already told you in the previous class, finding the Green's function is the most tedious task for the MoM. So Green's function would be different for different kind of structures, different kind of analysis you are doing. So here your Green's function has changed. Green's function for free space is exponential minus j beta r by 4 pi r. For this wire antenna, this whole thing is the Green's function. So we have already found out the Green's function. This is the most tedious task. After that, you can easily apply MoM. So let us go back to the equation. So I can find EZ it like this. So substitute what is AZ? AZ is this. It's a convolution of IZ with the Green's function for the wire antenna. Okay. What is this? This whole thing is your linear, looks like your linear operator. Anyway, let's see. So now EZ turns out to be like this. What is EZ? EZ is this whole thing operating on AZ. AZ, we have the expression for AZ. This whole thing operating on the AZ, this operator here, 1 by j omega epsilon 0 del square by del z square beta naught square, operating over the AZ. So this is your EZ. So I have EZ, I can write down the electric field integral equation now. What is the electric field integral equation? EZ scatter is equal to EZ incident when rho is equal to A. Rho is the radius. Rho is equal to A means when you have on the surface of the conducting wire. So the equation becomes like this. The equation becomes like this. We have the electric field integral equation. This is called the Helen's integral differential equation. We have differential also, you have also integration also. This kind of equation will be solving using the MoM. I have differentiation also, I have integration also. That's why we call it integral differential equation. And this is called Helen's differential equation. In the Poynton's equation, you actually take this operator inside the integration. So you have this operator here outside the integration. In the Poynton's equation, you take this inside the operator inside the integration, and it actually simplifies the analysis considerably. We will actually solve the Poynton's electric field integral equation for using the MoM. This is much more simplified. And You can calculate it. You can simplify this equation, and this person has done it. And actually, I have given this as an exercise for the BTech students also during their EM theory course. They could also derive this. So here you have one major simplification here, which is called thin wire approximation. In the thin wire approximation, this R here, R I've told you R you can derive it, R is square root of rho square plus A square. This, for the thin wire case, A would be very small, so this R value will become, whatever terms you have with the R, you can neglect it. R will be simply square root of rho square plus Z minus Z whole square. And usually you consider that the wire is very thin with respect to the L, or with respect to the lambda operating frequency wavelength. In that case, you can have thin wire approximation. This integration becomes very simplified. And later on, it can be observed that when you have thin wire approximation, your Green's function for the wire antenna can be simplified to that of the free space. Then your analysis becomes very simple. So Green's function for the wire antenna was very complicated. Let's just look at it. This whole expression inside the integration. So this Green's function for the wire antenna is like this: 1 by 2 pi integration from 0 to 2 pi exponential minus j beta r by 4 pi d phi dash. But when you apply the thin wire approximation, this Green's function reduced to exponential minus j beta r by 4 pi r. So that's a major simplification when you consider thin wire approximation, and it has been observed that this thin wire approximation is verified experimentally and it works well. So you don't need to worry that we are doing a lot of approximation. It has been experimentally verified in the literature long time back, maybe 50 years back. So let us look at the final integral equation. And the integral equation, the Polynomial's equation, you can refer to this example 10.4. 10.4 of, let's see, I have written a book on electromagnetic field theory. It has been given as an example 10.4. I have derived this. And you can simplify the Polynomial's equation to this equation here. So this is what we're going to solve. So here, we don't have any differentiation. I have taken care of the differentiation and simplify the Polynomial's equation. We just have an integral equation. Now we can solve it using MoM. How much time do I have? Okay, I can wind up here.